Okay, so assignment 5 deadline is today, and assignment 6 deadline will be next Wednesday, and assignment 7, don't worry too much about assignment 7 because you have your midterm on 14th. I think we now have a little bit more clarity. We know the later we do it, the more trouble we might face. So our original plan is to have the midterm on 14th. This is what we agree on at the beginning of this lecture, this course, right? Lecture 1. Originally, I wanted it to be on week to be on 9th, but then you say you have a clash with other course, so we defer it to 14th. So this is the date that we will do the midterm. Okay, and we are going to use the class hour, so which means well, try to be try to show up earlier if you can. That's to say, we are going to try to start the midterm at 11:30. Okay, so if we can do it like this, then everything will be nice, and it will be just like a business as usual, really. In case you have difficulty with this midterm, please let me know, and I will try my best to accommodate. And we also come up with a hybrid assessment scheme. So let me explain quickly. So you should see this as official because I announced it in the class. So we will have two options for the assessment scheme. So option A will be this. We are going to do a homework 20%, homework, and midterm 30. This is midterm. And then final will be 50. This is the original plan. And I proposed to the department that I also want to have option B to cater for those students who cannot come for the midterm. So actually, this is based on our discussion in the class. So in that case, I have the permission to raise the homework to 30, and then final to 70. Okay, so this should reduce your pressure a little bit. Otherwise, you will be faced with 80% final. In case you cannot do midterm, our usual practice is to shift the score to the final, right? Even for other courses, I believe this is our usual practice. So now, if you cannot do okay, I get the 3051 midterm change to 14. This is something I cannot help, because I changed it because some of you told me you cannot do 9th, right? So I changed to 14. Remember this? I think this is what you guys told me. So in this case, you should talk to the course teacher of 3051 and say something about this, because we agreed to change based on was it 3051 too at the beginning of the lecture when you asked me to change? Was this the same course? Okay, now in this case, it's better if you tell the course teacher. 3051 is Emily Ching, right? Professor Ching. You can tell her about this. You say I changed because of this. I even put it on the website. If you look at the course website, I crossed out this original date, although I didn't write the reason. Okay, so if this is it will be better if you relay this information to the course teacher of 3051. Okay, let me continue here. So these are the two options, and then to make it even better for you, we are going to count the best of the two options. Do you understand me? So if you take homework midterm final, if you take homework midterm final, towards the end, we are going to count all the scores using two schemes. and we are going to report the best score. Okay, it's a very simple exercise for us. That's to say, hopefully this will reduce your pressure about midterm. You can also see the other way. If you do not do well in the midterm, and you do very well in final, your score will be based. You have probably option B. So we are going to use just two simple schemes and choose the best score for you for the grade assessment. Okay. But I still encourage you to take all this assessment seriously. I try to be as flexible and as kind to you as possible. So I would like you to respect my course. Okay. Do you have any question about this? But one thing that will break my heart is this: you come to the midterm and then just draw a lot of Mickey Mouse, and then in the end, I do not know what you are trying to do, what you have learned. That is not nice. Okay, so just take my course seriously, and then we will get through this course together. Okay, finally, do you have more questions? If not, I want to continue. For the 3051, may I know what's the time for the exam, the midterm? I know the date now, but what is the time? Morning 9:30, 9:30 to 11:30. Okay, I will have to tell Professor Ching about this, because I would like you to come to my exam. Even if you cannot come on time, I do not want you to be late. Okay, so I will. You can also do the same. Please alert the course teacher. We need to sort this out. Okay, let's begin. One more question. If I switch back to 9th of March, is it okay? This is a date I want. I'm not saying I definitely want to switch back to my original plan, because I want to explore all options. Okay, so student Wu, if it's 9, you cannot, but 14 you can, right? This is based on my announcement. Yeah. Okay, I will see what Professor Ching can do. Because now my concern is not just having the 2 exams on the same day, but we have 2 exams back to back. So it's you know, for online exam, the time to scan the answer, to upload the answer, to release everyone, this can take a long time. So I will have to discuss with Professor Ching. All right, let's next Monday I will have more information. But again, let's continue, and then meanwhile, just assume the midterm will proceed as usual. We have even more clarity today compared with just yesterday. All right. Okay. So last lecture, I began to talk about this, the case of a different thermodynamic system, rather than sticking to PV system. We began to talk about this elastic rod. So I asked this question: if you have an elastic rod, so if I draw it like this, if I have an elastic rod, I don't know, this picture is not good. If I take a wire with a cross-sectional area A, and apply the tension F. So this is a cross-sectional area, sectional area. And this is what we have, right? We need to modify the first law. So the first law will be the d bar q term, we cannot do anything, but the d bar w term, we need to modify according to the realistic situation. And in this case, we are talking about a tension and the change of the length, dl. And then we define strain and stress as shown here. And these are really just a very common sense definition. We want to look at how the infinitesimal change of length, we want to normalize it to the length, and this quantity we call it strain. And from here, you know we have the stress and strain relationship that allows us to define an elastic modulus, and that elastic modulus is the Young modulus appropriate to this system. Right? You can have bulk modulus, you can have other moduli, but for us, for this situation, this isothermal Young's modulus is what we want to look at. Then I define this alpha F, which is very, very similar to how we define the beta case for PV system. So this is the thermal expansion, volume thermal expansion coefficient, which we defined earlier. And now you can see what is the force in the PV system. I told you pressure plays a role like a generalized force, and here the force really is the F, the tension. Okay, so we have a constant pressure. You didn't complain, and now you shouldn't complain too much. There I can define alpha sub F. Now, how do you do this in reality? You can also imagine this, right? I can take a wire, I can put a little bit of mass on one end, and that will keep the tension. And then I can change the temperature and look at how the length change. And there will be this quantity alpha F. Okay, so alpha F tells you how readily the length can change when the temperature is varied under the condition of constant tension. Okay. So now this is where things get interesting. So if I copy this and get rid of this picture, I hope you have managed to find some rubber band. Okay, here. Now, what do we have? We need to discuss a few things. This is still thermodynamic. We might not be able to give very quantitative prediction, but we will be able to gain something here. At least we can talk about the sign, right? What is E sub T? So this is isothermal Young's modulus. Now, for you, maybe it's more intuitive to think about the inverse, right? So this partial F, partial derivative of F with respect to L, maybe it is difficult to appreciate, but you know your reciprocal theorem. If you want to discuss the sign only, you can also imagine the situation when you apply tension, what happens to the length. Okay, so that will be the inverse of that. Okay, and in this case, if you pull something, it becomes longer, and therefore this is a positive quantity, right? So this is this E sub T is always positive, always positive. And when you pull, why? Because when you pull the wire, it becomes longer. Okay, and then the other thing is the other quantity which we obtain today is this alpha F, and this alpha F. And this alpha F is the interesting part here. So what is the sign of the alpha F? Okay, I'm going to give you now the point is alpha F can have can either be positive or negative values. Okay, can either be positive or negative. Okay, can either have positive or negative values. So I say in general, okay, this is a general case. In general, if I have alpha F for a metallic wire, this is usually positive for metal. Okay, and you can actually imagine the situation when I have alpha F to be negative. And that is, for example, for the case of rubber wires. Okay, I say this is usually, we need to be careful here. So if I have some really smart material, I can design my alpha. Okay, and if I just talk about standard materials, rubber, typical metal, and I can have something like this. Okay, this is kind of cool. Remember, what is alpha? Alpha is when I apply, when I raise the temperature, the length, how does the length change? If I increase the temperature of a metallic wire, it gets longer. But if I take rubber and then raise the temperature, it can get shorter. Okay, do you understand this? This is alpha. So for the negative alpha, this is the interesting thing. Okay, so now I want to actually convince you that this is a case. So I'm going to burn some rubber in my office. And in order to do that, I want to switch off the recording. Okay, I'm going to switch on my camera and I'm going to switch off the recording. So are you ready? How many of you are here? Okay, do you want to see? Okay, let me pause the recording first, resume the recording. Okay, so you have seen this experiment and I hope you are convinced that this is possible. The second scenario is possible, okay? And now there's one more quantity I want to ask. Now you have seen two partial derivatives here. So here, what are the two? Actually, these are the two, right? This E sub t is related to the partial derivative. And this is the Young's modulus, and this is a partial derivative describing the change of the length. And now let's look at this, right? So you see you have the quantity of interest are F, L, and T, right? F, L, and T. So you already have something like constant tension, constant temperature. But you, with these three variables, you have one more possibility, and that is a partial derivative keeping L constant. Okay, and that is the third one, the third quantity. Okay, so that is the one I want to ask. That is a partial derivative. Written like this. Okay. Now, how do you imagine this quantity? What is this quantity? And this quantity is the following. Suppose you have you have a wire fixed between two walls or two supports, right? So for example, I take a string and I keep these two, the separation between the walls are constant, right? So I will have a constant L. I have a constant L. Okay, and I can ask myself this question: if I raise the temperature, what happens to the tension of this wire? Okay, now this is a question that if you play some musical instrument, this should be something quite intuitive to you, right? So for example, you take your violin or your guitar, a string instrument. You have a system like, you have a situation like this, because the string will be fixed between 2 points, and then you adjust the tension for tuning. So for example, you tune your guitar at somewhere very, very hot, and then you enter your concert hall to do your performance, and you will find that maybe the pitch will change, right? This is kind of intuitive, right? I don't know if there's any of you play this kind of instrument, you can confirm to us whether this is the case, right? You have to tune your I don't play musical instruments, so I can only use physics to try to understand this. If you tune your instrument and if you change your room temperature, there's a chance that you have to tune the instrument once again before the performance starts, right? So there is this quantity here. Okay, so we need to learn how to describe this quantity, and this quantity, how do we relate this quantity to the other two partial derivatives? And that is something you learned before, right? So you do, you apply reciprocity theorem. So this is reciprocity theorem. Okay, so reciprocity theorem always comes with a minus sign. So let's put this minus sign first, and then you just I'm sure you can verify this yourself. So this is the outcome. Okay, so you have T, L, and F. Okay, so if you plug in the definition of all these in terms of alpha and E sub T, then you get something like this. You have minus E, T, A, and then alpha F. Okay, this is really just plugging in the definition. Okay, and now if you have a metal wire, again you look at the sign, you know this is always positive, but for the metal wire this is positive. So if you raise the temperature now for the metal wire, so this quantity because of this minus sign, this quantity is negative for metal wire. And for rubber wire, it will be positive. And therefore, if you have a metal wire, if you raise the temperature, in this scenario, tension will go down. Okay. Is it anyone playing violin or guitar here? Anyone can confirm this? Right, so if you have such a scenario, the pitch will go down, right? When temperature goes up, pitch will go down. Okay, thank you. Someone say yes, so let's trust that person. All right, so the thing I want to analyze is this situation. I also asked you to find a rubber band. Okay, so this is the answer I want. This is the part of physics I want to extract. So what is this experiment? The experiment is the following. You take a rubber band. So let's say you take a rubber band, right? A thick one, like the one I showed in the beginning of the lecture, and you cut it like this. And what I want you to do is you pull. You take this rubber band and you pull as hard as you can, but with a lot of care, as hard as you dare to do it. Okay, and when you pull, doesn't need to be very fast, but do it reasonably fast. And after you put a lot of tension, you immediately put this rubber band on your lips. Okay, the idea is your lips can sense the temperature. Okay, and you want to do this process fast enough before the rubber band reach thermal equilibrium with the room. So that is the reason why I want you to do it fast. So you pull and then you immediately put it on your lips and you will feel that the rubber wire will be hot. Okay, and the reverse, you can also do it this way. You can pull and then you keep this tension for a long time. Why do you want to do that? Because you want to reach thermal equilibrium with the surrounding. Okay, and then you release the tension, and that moment you put it on your lips, you get the reverse. You feel that this rubber band is cool. Okay, it's colder than you expected, and that is the reverse. Okay, and how do you get this? How do you explain this physics? This is how. Okay, so to explain this, we need to write the Helmholtz function. Okay, Helmholtz function F is U minus Ts. And therefore, dF is du minus TdS minus S dt. We already rewritten our du. Okay, so now we still have TdS term, so TdS cancel TdS. I have S dt. And I will have the term which is related to our situation here. Okay, so this is the tension times the infinitesimal change of the length L. Okay, and why do I care about this? The reason I care about this is because I don't want to stop here. What I want is to look at the Maxwell relation. So the Maxwell relation appropriate to this thermodynamic potential function will tell me exactly what I want. So this is the first order differential of F. So Maxwell relation wants me to go to the next order differential. So here I already differentiate with respect to T, and the next order differential I will differentiate this with respect to L. Okay, and keeping T constant. And there's a minus sign, so I put this minus sign to the other side. So here I will have this F, which I will evaluate the second order differential, and this time I have to differentiate with respect to T, and keeping L constant. So this is my differential. All right, and now you understand why I want this quantity here. Okay, because this quantity is related to what I want here. Okay, so I plug in everything. I just simply have a change of signs. I have E, T, A, alpha, F. Okay, so now I'm ready to answer this question. So here we go. So this is the last line is what I want. I will do it thermodynamically, and I would like you to think microscopically. Okay, so I will tell you thermodynamic tells me I will have this result. What result? So for rubber, for this rubber wire, rubber band. So for rubber band, now I will draw this picture for you again, just to remind you this this is related to this experiment I asked you to do. So for this rubber band, I will have this analysis. So for the rubber band, cut it into the form of a wire. I will have E sub T is positive, alpha F is negative. So therefore, according to my analysis, this has to be negative. Okay, so this has to be a negative quantity. And this negative quantity tells me if I pull, when I pull this rubber wire, entropy goes down. Okay, so when I pull, so S decreases when I pull. Okay, so what does it mean here? So entropy goes down. How can the entropy of this system goes down? it has to be able to exchange heat with the surrounding, right? So I pull this rubber band, some entropy leaves the system. So it will leave in the form of heat. And therefore, when you pull, you put it immediately on your lips, you will feel hot. Why is it hot? Because because heat leaves the system, and this basically is a heater. Okay, this effect is not too difficult to see. Your lips is able to detect this temperature change. The harder you pull, the larger the effect will become. Okay, so this is what I want to describe. And you have the inverse situation is if you pull, let it reach thermal equilibrium, and then now you shrink it back. That's to say you reverse the process, then entropy will goes up. And how do the system gain entropy? It gains from the surroundings, so you have to supply heat. Okay, so this is what thermodynamics tells you. And the question is why. So the question is why. And this is something I would like you to think about. So why? Okay, and think first. And if you cannot, then I'll give you some hint. So you can look up Blundell and Blundell. Blundell and Blundell has a nice cartoon on this. Okay, so that is what I want to say about rubber band. Okay, next part is we don't need this anymore. It's a magnet. A magnet is also interesting. So you know about rubber band now. You know about you will see how I deal with magnet, and I ask you to think about the reason behind this. Right, this is the last question I pose, and eventually I want you to unify the three systems. One is the rubber band, then the paramagnet, then your gas expansion, the PV system. Okay, so when you do isothermal expansion, what happens to the entropy? Right, so and then what is the reverse? You have isothermal compression. What happens to the entropy? Right, so these are all these are actually the same physics. Okay, so the magnet is a complicated system actually. You can have a lot of different types of magnets. So here we are going to talk about a particular type which we call the paramagnet, which means it doesn't order. Right? It's not like your fridge magnet. Your fridge magnet is what we call the ferromagnet. Right? You have the ordering of all the moment. Okay, so here we are going to treat the simple case, and even for the simple case, we are going to already learn a lot. Okay, and as the case of the elastic rod, we need to begin by looking at the first law. You have a new thermodynamic system now, so I need to look at the first law, and this will be related to how you perform work on the system. D bar Q is always the same. Okay, so in general, this is related to the magnetic moment. Right, this m, little m, is the magnetic moment dotted with the magnetic field. Okay, so even this is already quite tricky, right? So what do I mean by the magnetic field? Which kind of magnetic field am I talking about? So here I need to make a further assumption. I'm going to assume the moment can only align either parallel or anti-parallel. Okay, so if it aligns, it will align either anti-parallel or parallel, and that will give me the work. Okay, so this is something to do with this dot product. That's to say, I want to simplify to just the product of two scalars. Another thing I need to talk about is what is this B? So first, this is I want to eventually talk about the interaction of all this magnetic moment in my solid, right? I have a piece of solid, and this solid is a paramagnet. I want to talk about all the interaction of the moment in this solid with the magnetic field I apply. That is to say, I do not want to worry about you see, you have a lot of moments in your system. In principle, other moments will generate its own magnetic field, and that can influence a given moment, right? So I pick a moment, the moment will see many moments around, and the other moments can also generate the magnetic field, and that can also influence this moment I pick. Okay, but this is the interacting picture. So we are going to ignore that problem. We are going to assume the dominant effect is coming from the external field. Okay, so in other words, we are going to treat this as non-interacting system, non-interacting magnetic moment, arranged in the lattice of a solid. Don't worry too much about this this term lattice. This has very strict definition in solid state physics. So let's just say I have a piece of material. I know there are moments inside, and these moments are not randomly drifting. These moments are very on a very regular array of sites. Okay, so and now we can apply the field. Okay, and the idea of this magnetic field is this external magnetic field is when I apply the field, I can cause the alignment of the moment. Okay, so if I apply field, I can cause the alignment of the moment. And therefore, my first law becomes TdS minus M. I will drop the dot product between two vectors. I will just use the simple multiplication. Then that is enough for us to get what we want. Okay, and even at this point, we need to talk about what is the meaning of this B, but this is quick. In your EMN course, you know there's a B field, there's H field, there's M magnetization. And in the most strict sense, we should differentiate between B field and H field. Okay. And if I do it this way, let's use the strict definition. And in this case, I would have to call this magnetic induction. Okay, and the field I apply is really called the H field. So in this case, this is magnetic induction, and B is the magnetic induction, H is the applied field. Is the applied field. But for our situation, they are practically equivalent up to a constant. The reason is this: we have a paramagnet. Okay, so if I write you the relationship between B and H, this is the relationship. You have B is B mu naught H plus M. Okay, so this capital M, this is lowercase. So this capital M, I will put like this. Okay, we must not confuse. I'm going to make this very sharp and pointy. Okay, this capital M is called the magnetization. And if you have a paramagnet, this magnetization is very small. Okay, that's exactly what I say. We are not talking about a ferromagnet where your magnetization is very large. Okay, so for a paramagnet, this M is very small. Is small. How small? Small compared with the magnetic field you can apply. Okay, so this is a small quantity. Let's just take this as a small quantity, and you immediately get the result I claimed. Okay, it's just these are just some linear relationship up to a multiplicative constant. Okay, how do you relate this big M to the little m? So the little m is what we call the magnetic moment, right? I wrote it up here. So this little m is related to the big M magnetization simply by the volume. Okay, so magnetization, in other words, magnetization is the total moment per unit volume. Okay, so this is the magnetization. And this is the volume, sample volume. And this is the moment. The little m is the moment. Now, when we talk about magnetism, a quantity which we often use is susceptibility. So I'm going to introduce one more quantity. These are all definition. Okay, I need all this, and once we finish all this, we can get the result very quickly. Okay, so I need to introduce magnetic susceptibility. Okay, this takes a symbol chi. So chi tells me how easily it is to induce magnetization when I apply a magnetic field. Okay, so if I change this to the mathematics, this is this ratio M magnetization divided by H. So how susceptible it is? So if I have two material, one is more susceptible to polarization, then I apply the same field, the magnetization will be larger for that material. Okay, so this is the meaning. And we also like to look at this at the low field limit. The reason is this: if you apply very, very high field, you will have complete polarization. Okay, and that means you cannot polarize it anymore, and it's meaningless to discuss the susceptibility of that material in that case. So if we want to compare how easy it is to polarize the moment of a given material, we like to go to the low field limit. Okay, so this is the definition, and then plug in our approximation. That is to say, I want to use the B rather than H, then this will be written like this. Okay. Now in here, this is a nice picture coming from Blundell and Blundell. Now this part you will see again actually. So this is a very nice system, a very cute system that we can analyze it in statistical mechanics too. So this is exactly what we want to do later. We are going to learn partition function soon, and we are going to use this model system to repeat everything. And that's why do not forget this part. Everything you are learning now, you will see again, but from a different approach. Okay, so this is kind of a little bit more extreme case. So suppose you are at high temperature. So the idea is this: I'm going to write without proving that the chi, this susceptibility, has this temperature dependence. Okay, so at high temperature, the susceptibility will go. At high temperature, susceptibility is lower. Okay, why do you have this? You can kind of use this picture to understand what happens. So at high temperature, because you have thermal fluctuation, this thermal fluctuation compete with your magnetic field. Okay, so as I say, this is the extreme. It's just to give you a cartoon picture. So the magnetic field tends to align the moment. Okay, so if you get rid of thermal fluctuation, you have let's say you have very, very low temperature, and magnetic field will win. So magnetic field will try to align all the moment as it wants to do. At high temperature, you are not so lucky, even if the field is the same. At high temperature, you will see that the thermal fluctuation tends to randomize the moment, and therefore you will have less magnetization, and therefore susceptibility goes down. Okay, so this cartoon has to be interpreted very carefully. So at low temperature, you must not look at this as completely saturated, completely polarized. You should look at it as the following. Just think of it as a dynamic process in your mind. When I apply some magnetic field at low temperature, this magnetic field, this same magnetic field is very effective to align the moment, and that will give you large magnetization, and therefore susceptibility is large at low temperature. Okay, so I will write this down. This is Curie's law. Okay, I write this down without proving, but I'm going to show you this Curie law maybe 3 weeks later. Okay, so we are going to see this again, and I want you to recognize that, wow, this is really something we can extract from by analyzing the microscopic detail of the system. All right, so Curie law, and now at this moment I will give you the intuition behind. The intuition is because you are competing with thermal fluctuation. So thermal fluctuation will tends to randomize moments. Okay, and therefore I have one partial derivative already. This partial derivative is this. Okay, so I can from this picture and the discussion, I can discuss at least the sign of this partial derivative, and this has to be negative. Okay, right? So this is suppose you are at some low field and you do this experiment. This is chi, this is t. You have some fixed field. You do this experiment. You apply some magnetic field low enough, and then you measure the susceptibility as a function of temperature. And this is this slope is always negative. Okay. Okay, what is the next step? The next step is to discuss the entropy again. Okay, I want to discuss the entropy. So you will see the treatment is parallel to the case of elastic band. I can write the Helmholtz function again. Okay, so Helmholtz function, I will just write the result. Okay, you will see the intermediate step is identical to the previous case. Okay, so this is my thermal term, and my work term is this. And after the writing down the Helmholtz, the next step is to do the Maxwell. And that will give me the entropy, right? It's very convenient. This Helmholtz function is very useful. Okay. And this is there's a minus here, so they cancel. I will have this result. Okay, this is good news, right? Because you can see I have something which is which I can relate soon. Just a few more steps, but you see I have a derivative with respect to temperature at constant B. And I want to tell you why I'm doing things. So you see, eventually my goal is to relate to this quantity, right? I don't want. Now, the little m is proportional to the big M is proportional to chi. So you know that they are, if if I'm careful to write out all the prefactor, I will be able to relate the change of entropy to this guy here. Okay, so that is my goal. Okay, I'm going to do exactly this. First, I will write it like this. Right? What is m? Little m is big volume. The big magnetization m times the volume. Right? So I will have this quantity. Now, this is a big assumption, but it's a reasonable one. I'm going to assume this volume will not change too much. Okay, so as a function of temperature. So that is to say, I ignore the thermal expansion. And that is a good assumption for solid. So I can pull this out and I will have this one. Right? Remember, for solid, in general, the difference between the heat capacities at constant pressure and constant volume is proportional to the thermal expansion square. Right? I argue that this difference is not significant for solid because we can ignore the thermal expansion in solid, or thermal expansion is very small, like one ppm, 1 part per million. So this is the kind of scale, and therefore we can safely ignore this. Okay, so I will make a remark here for you. So I assume this to be a assume constant, which is very, I would say, okay, I will be a little bit more conservative. I would say a fair assumption for solid at low temperature. Okay, let's don't worry about heating this to 1000 Kelvin. We are not talking about that. Remember, in the end, I want to develop the physics of cooling. Okay, so coming back to here, let's tidy everything and we will have what we want. We will have this result. So this is this guy. I will copy once again, a little bit tidier. And my goal is to relate this to chi. Okay, so I have magnetization which is proportional to chi, and the proportionality constant is the magnetic field B and the mu naught, and I have this. This is what I want. Okay, and this quantity, we can discuss the sign, right? Because I told you this is always negative, this slope, right? Chi, because of the Curie law, right? So this gives me this result. Okay, so this is this has a reason behind. Why do I have this inequality? That is because of the Curie's law. Okay, so this is a nice already. If I apply magnetic field isothermally, what happens to the entropy? Right, so I want you to compare this with the case of pulling a rubber band. You have a differentials that look like that, right? So you have isothermal case over there. You have the change of entropy, but there you are talking about the change of entropy with respect to the length, right? So there you have now look at this. You have partial S, partial B at constant T, and there you have partial S, partial L at constant T. And again, at the level of thermodynamics, we can discuss the sign. I ask you why, right? But here, you have something similar, and I'm going here. I want to explain to you why. Okay, so now I still want you to think about this. I propose we take a break now and come back at 1:45, and we are going to pick up from here. Okay, so see you at 1:45. Once you come back from a toilet, you can start to think about why I have this result, the very last line here. Okay, see you soon. Welcome back. Okay, so before the break, we obtained this result. This is the change of entropy with respect to a magnetic field. So I told you this is a negative quantity. When you apply magnetic field, so look at this, when you apply a magnetic field, entropy goes down, right? So this is how you should interpret this. If you apply, if you increase, okay, let's be more precise. If you increase B field, S goes down, S decreases. Okay, so this is something you can readily appreciate. So how do you appreciate? You look at this picture here. Okay, and suppose you are at the same temperature. Let's say you are at the same temperature, right? Then you have an intermediate case. These are extreme cases. Let's say you start from some temperature and you have the case A, and I stick at that temperature and only change the magnetic field. That is the meaning of this constant temperature, right? I keep my system at the same temperature, but I use the magnetic field to manipulate my system. And when I increase my magnetic field, the moment will tend to align. Okay, so when the moment, suppose in the extreme case that they are all aligned, then they don't have any more freedom to explore because they are pinned to a particular direction, and therefore entropy goes down. And if you decrease the magnetic field, suddenly you all this moment have a lot of freedom to explore. They can align with at a random angle. So in this case, intuitively, you should expect the entropy to be high. Okay, so that is the reason that you can expect this. And the question I asked you to think about the rubber, the related question actually has the same sort of argument. So when you look at a rubber, what happens inside? And when you look at a metal, what happens inside? Okay, so if you have a little bit of knowledge about the polymer physics, you'll be able to also discuss this. Okay, so similarly, if you have if you pull the rubber and put on your lips, you can feel the rubber is hot. That's because there's some heat exchange, and here similarly there will be a heat exchange. So here I will write it. Okay, the heat exchange is given by, I want to relate to this quantity here, this partial derivative. So you know heat exchange has to be heat is TdS, right? So if you have this quantity, how do you relate this quantity to the heat? Okay, so if I have TdS, that will be that will give me the unit of Q, right? The energy. But there's not enough. I have this magnetic field. So the way I should look at this is I can relate how, if I increase the magnetic field by this amount, if I know this partial derivative for a given system, a given magnet, I will be able to calculate how much heat I will gain, depending on whether I increase or decrease the magnetic field. Okay, so again, just put everything inside. I will have this quantity which you can play with. This is rewrite everything in terms of susceptibility. Okay, and of course delta B. Okay, I need one more quantity, then we can discuss cooling. So I want to box a few things first. We are going to come back to here. This is the quantity I need you to keep in mind. This one, the sign of this. Okay, we want the sign of this. And then I need one more. I need to develop one more. Then we are ready to cool. Plus. Okay, the other quantity I want is this. I want to ask what is the change of temperature with respect to